this video, I'll go over the different ways the Data Baker, part of my Game Tools Blender extension, can be used. This tool is essentially a version 2 of my old Data Baker add-on, which I showcased in a video about 2 years ago. Some of what I covered in that video is still relevant to this newer version, so it might be worth checking out, but it's definitely not required. The tool also comes with extensive documentation that explains its purpose and showcases a few use cases. This video is meant to complement the wiki and content examples. Alright, here I have a small test scene made up of a few cards to create some kind of grass asset. Nothing unusual. Each card is a separate object with its own position, orientation and so on. This becomes relevant depending on the type of data you want to bake. In short, this tool is somewhat similar to the Object Attributes Baker tool, in that it also bakes object attributes like position, axis and many other things. The Object Attributes Baker, as demonstrated in previous videos, stores data in textures, along with parent indices that can be used to recreate a hierarchy. This allows the shader to sample the parent data, then the grandparents and so on. The Data Baker, however, works differently. It bakes directly into UVs, vertex colors or even normals. This approach no longer supports hierarchical sampling. You only have access to the data stored directly on each vertex. In other words, when processing a vertex of a child object in the vertex shader, there's no way to quote-unquote look up the corresponding data from its parent object. This is clearly a more limited approach compared to baking into textures, where you can store virtually any data and use indirect sampling to navigate complex hierarchies. However, it's often a more efficient solution for many practical use cases. For example, with most simple foliage assets, a hierarchy isn't necessary. All the required data can be baked directly into UVs, vertex colors, or even normals. Say you just need to store pivots. There's no need to bake that into a texture, create a dedicated UV map for sampling, and then fetch the data in the vertex shader. Instead, that information can simply be baked into the UVs. The idea is straightforward. Let's say you have a mesh and want to store its X and Y position. You can collapse all the vertex UVs and assign them the corresponding X and Y values. Since UVs are stored as 16-bit floats, they can represent a wide range of values, positive or negative, large or small, far beyond the typical 0 to 1 range we usually stick to when preparing UV maps for texture sampling. But when using UVs to store arbitrary data, that limitation does not apply. You can store virtually any value, 16-bit floats precision issues aside. If you also need to store the Z position, you could create another UV map and use the U component for storing it, leaving the V component free to store additional data. That's the basic idea. It's simple, but it can be extended much further to store more than just position data, using techniques like bit packing and more. I'll cover that in a future video. For now, let's start simple. This tool introduces a new concept I call data layers. So let's go ahead and create a new layer. It's automatically named based on the data type and various settings. The add operator is also somewhat smart. It detects the currently selected data layer and creates a new one based on it. For example, if it detects that you're baking the X position, the new layer will automatically be set to Y. The same goes for the target UV map and component. They will increment accordingly. And just like that, with 2 clicks, you can bake the X and Y pivots for your mesh. Click Bake. Import the mesh into Unreal Engine. Create a material. Use the texture coordinates at index 1, that's where the pivots were baked, right? Append a 0 for the missing Z component. Create a rotate about axis node. Rotate the vertex local position. Plug in the pivot. Create a scalar parameter for the rotation angle. And then convert the local offset to world space and plug it into the world position offset. And there you go, each card rotates around its own pivot point. Very cool. Baking the Z position is just as straightforward. Select the position Y layer, then create a new one. The position will be set to Z, and the UV map will switch to 2, storing the value in the U component. Once the baked object is exported and re-imported into Unreal, that extra UV map can be sampled to retrieve the Z coordinate, allowing you to reconstruct the full XYZ pivot. Now, there are a couple of important things to mention. First, Blender uses an OpenGL coordinate system, it's right-handed, while Unreal Engine uses DirectX, it's left-handed. This means that v equals 0 in OpenGL corresponds to v equal 1 in DirectX. To account for this, a 1 minus operation is automatically applied to the v component during the bake, since Unreal Engine will apply that same transformation automatically when importing an FBX file. Second, Blender's default unit is meters, while Unreal's is centimeters. That's a factor of 100. And it's also handled automatically during the bake, so you don't have to worry about unit conversion when reading the UVs in the vertex shader. Third, the position baked into the UVs is in world space in Blender, but it becomes a mesh's local space in Unreal Engine once imported. I've gone over this in more detail in a wiki article, but I'll briefly cover it here. The card pivots baked into the UVs are relative to the static mesh's own pivot point. They represent an offset, not an absolute world position that includes the static mesh transform, hence the need for the transform vector node. And it makes sense. In short, if an object's baked position is say 500 cm on the x-axis, that's what will be stored in the U component of the UV, right? But if the static mesh itself is offset by another 500 cm on the x-axis in the world, then the object's position is actually 1000. The UV will still read 500 though, and the transform vector node is what accounts for the mesh's world transform, converting that 500 into 1000, which is the true world position. If that sounds confusing, feel free to check out the wiki for more details. Anyway, enough of that. Most data types expose a source option, similar to what's available in the Object Attributes tool. By default, the tool bakes each object's own attributes, self, but you can choose to bake the attributes of the object's immediate parent, if it has one. If not, it falls back to self. You can also set a custom object as a global override, or use an object pointed to by a custom property if defined on the object. In most cases, self is the most common and sensible choice. When adding new layers, the tool should automatically update the UV map and channel to avoid conflicts, but you can still adjust these settings manually if needed. Of course, manual adjustments can lead to conflicts, like two data layers writing to the same UV map or channel. If that happens, a warning icon will appear and the bake will safely fail with an error message prompting you to resolve the issue. UV maps are the most common way of storing baked data. Data can also be stored in vertex colors or normals, though each comes with limitations. I'll cover those in more detail in the next video. In brief, vertex colors are supported, but due to their limited 8-bit precision, values must be remapped and precision may be limited. Normals are also supported, but are even more constrained and should only be used in very specific cases. Alright, what else? In most cases, you'll want to preserve the original materials. You'll also typically want to duplicate the selection and merge the result to generate the baked object. You can keep objects separate for further editing or bake directly onto the original selection, but be careful. This can cause issues, especially if objects share data or use modifiers. Also, the data baker uses attributes internally to store temporary data. These serve no purpose outside of the baking process and should be cleared most of the time. They can be kept around for debugging or obscure workflows, but they won't affect FBX export since attributes aren't part of the exported data. Most of the time you'll want to clear them. As mentioned earlier, the V component of the UV should be flipped if the target application uses a different coordinate system than Blender. Since Unreal has a different orientation, this option is enabled by default. Your blend file must be saved for the export settings to become available. Once saved, you can specify an export path. After baking, the tool generates a detailed report with useful information. This report is also saved as an XML file, which can be helpful if you want to build a custom importer for your application or game engine. And that's most of it. Before wrapping up, let's do a quick overview of the data types you can bake. Position, well, that's pretty straightforward. just store the desired components in different layers. Axis, same as position, pick an axis, X, Y, or Z, and store its components in 3 different layers. Shape key, it lets you bake the offset or normal from a shape key. Enter the name of the shape key, then choose whether to store the X, Y, Z offset and or normal into UVs, vertex colors or normals. This data can be easily sampled in a vertex shader and reapplied, as demonstrated in the content examples. I'll go through those examples in an upcoming video. Mask. It allows you to bake linear or spherical gradient. You can choose the origin of the mask, world origin, the object's own origin, a custom origin object, the average center of the selection, and the object's parent origin. The gradient can be based on actual units, measuring how far each vertex is from the origin, or normalized to the 0-1 range based on the furthest point. When normalized, the gradient can be modified using a power curve to make the transition non-linear. Random, this one's interesting, but a bit trickier to use. You can generate random values per collection. All objects in the same collection share the same value. Per object, each object gets its own random value. And per face, each face gets a unique value, but with consequences. Per face random values require each face to have unique UVs, which means duplicating vertices. This is an expected technical limitation explained in detail in the wiki's technical compendium. It's not an issue in per object or per collection modes. Now, random values can be a single float, a float 2, and a float 3, or vector. Here's where it gets more advanced. If you want to generate, say, a random float 3 per object, meaning a random unit vector per object, and store it in the normals, you need to create 3 layers. Set each one to type random, mode per object, format float 3, storage normal. Each layer stores one component, X, Y, or Z, of the vector in the corresponding normal channel. A seeding system ensures that all 3 layers generate the same random vector, so the X, Y, and Z components are consistent and come from the same source, if that makes sense. The same approach applies to float 2 values. And technically, storing a single component of a float 2 or float 3 is no different from storing a regular float. That said, there's also a useful setting called uniform when generating float values. Let's say you have 10 objects and generate a random float for each. Due to the nature of randomness, you might end up with values that cluster around 1.0. Not ideal if you want full range coverage. And that's where uniform comes in. When set closer to 1.0, it forces the generator to evenly distribute values across the 0 to 1 range. With 10 objects, you'll get 10 values, evenly spaced by 1/9, and they'll be randomly assigned, ensuring full coverage. This helps make your random values more balanced, I'd say, and it's highly recommended for most use cases, like assigning a unique random offset per grass card for wind animations. It just works better with uniform randomness. Anyway, that's it for random. Value is super straightforward, it simply bakes a hard-coded value. Custom property works on a similar principle, except instead of using a fixed value, it pulls the value from a custom property stored on each object. That property must be of type integer or float for the bake to work. Frame might sound a bit cryptic, but it's essentially similar to shape key. Instead of specifying an actual shape key, you provide a target frame. The bake then computes the vertex offset and or normal of the mesh at that frame relative to the current frame. So in practice, it behaves a bit like a shape key, but the deformation is stored on a specific frame rather than in a shape key. This could be useful in some niche cases. Depth stores an integer indicating how deep an object is in the hierarchy. A root object gets a depth of 0, its child gets 1, the grandchild gets 2, and so on. Finally, Quaterion stores the object's rotation as a quaternion. You can choose to bake the quaternion's X, Y, Z, and W components separately, but that requires 4 channels. Alternatively, you can use bit packing to store all 4 components in a single 32-bit float. This method only works with UVs since normals and vertex colors aren't well suited for storing precise bit-level data. That said, even UVs can pose problems because of how Unreal Engine handles the V coordinate. As mentioned earlier, Unreal automatically flips the V channel on import by performing a 1- operation. And if that V channel happens to contain a bit-packed float, this operation scrambles its bits and corrupts the stored value, effectively destroying the data. Because of this, bit-packed quaternions should only be stored in the U channel, where no such modification takes place. One last thing, you may need to swizzle axis specifically when storing quaternions, and this option allows you to override the axis order global setting specifically for quaternions. And if you're storing the quaternion components across multiple data layers, make sure the axis swizzle settings are consistent across all of them, otherwise the resulting quaternion will be incorrect. And that wraps up this brief tour of the tool. There are lots of possibilities to explore. I'll dive deeper into the bit packing feature and more in the next video.